So I'm Benjamin Palmaerts from ISSeP, the Scientific Institute of Public Service in Belgium, which is a partner of the Working Group Africa. And I'm going to present here a use case using Sentinel-2 data for Burkina Faso. Oops. Yes, so the work I'm going to present here was mainly achieved by David van Rossum, who did an internship at ISSeP last year during a couple of months. And the goal of his internship was to develop a free and open source method to remotely monitor the water reservoirs in Burkina Faso. He didn't consider the whole country, but already a large area, actually the watershed of one of the main rivers in Burkina Faso, the Nakambe River, also called the White Volta. Just in the Nakambe watershed, there are around 900 water reservoirs, so which are small artificial lakes created with small dams or dikes. Most of them are smaller than 20 hectares. And they are shallow, which means that there is a high risk of drying out. But at the same time, there are sometimes heavy rainfalls in Burkina Faso, meaning that there are large variations of the water volume over a very short time. So why are there are these reservoirs? So mainly for agricultural production, sometimes for irrigated cultivations, also for vegetable growing, livestock watering, and also for fishing and for supplying with drinking water. But there are some issues with these reservoirs. As I mentioned already, there is a high dependence with the weather. Also, there are many sediments coming from the whole watershed, leading to silting of these reservoirs. Then the level of the water can drop quite rapidly because of overexploitation of these resources. And the water can be polluted by phytosanitary products like fertilizers from agriculture. And because of all these issues, there are conflicts between the users of these reservoirs. So there is an interest of developing a tool to monitor the water resources in each reservoir individually. But of course, there are some important challenges. So we wanted to have a tool which could be used by the potential users, which have sometimes limited computer infrastructures. If you consider large areas and the monitoring over a long time, then you have a large amount of data that you need to process. As I mentioned also, there are these short scale variations over very short times. So you need to have a good temporal resolution for your tool. And with EO data, of course, we have information about the surface of the reservoirs, but you don't have information about the volume of the water content. And of course, you need to also to deal with the clouds on the images. So the solution we tested was to use a Sentinel-2 data within the Copernicus dataspace ecosystem, which was presented in the previous talk. And we developed Python scripts on the Jupyter Lab provided in this dataspace ecosystem. So what David did was first to subdivide the watershed into a grid to not deal with region too large. So he considered only a small cell of this grid as a first step. And then he used the OpenEO API, which is provided in the Jupyter Lab of the dataspace ecosystem. And with this OpenEO, it's very easy to download the data. So when I say download, it's not download on the local computer. What is interesting here by using this Copernicus dataspace ecosystem is that everything is done on the cloud, all the acquisition of the data and the processing of the data. And so with just these few lines here, I'm sorry, it's written in French, but of course the comments are in English. You can just specify the temporal extent that you want. Here it was 1 month. Then the satellite the type of data that you want to use, then the spatial extent of your area of interest, the coordinate system you want to use, and the bands you want to use. So it was the 3 visible bands and the near infrared band. There is also the SCL band that I'm going to mention in a few minutes. You can also select a maximum cloud cover. It was 50%, meaning that all the images with more than 50% of cloud cover over your area of interest are not downloaded in your Sentinel-2 cube data cube. So we use this SCL band, which is provided with Sentinel-2 data to create a cloud mask. So as I said, we use this filter of 50% maximum cloud cover. But if you have 40%, for example, a cloud cover, then you have some clouds in your image, in your area of interest. And so it's interesting to identify where are these clouds. And this scene classification layer is like an automatic classification of all your pixels of your images, indicating where there are wrong pixels, where there are vegetation. And in our case here, we wanted to know where are the clouds. So we took 3 classes from this scene classification layer. The class where there is this high probability of cloud, the class with this thin cirrus, which indicates where are these high altitude clouds, and then also the class with the cloud shadow. So for all these 3 classes, it's more difficult to detect the water because of the presence of these clouds. And then to detect the water, we use this spectral index NDWI. So there are actually 2 definitions for the spectral index. Here we use this one, so using the green band and the near infrared band, so the B3 and B8 bands of Sentinel-2. And so it's very easy from the image to calculate the NDWI directly on the Jupyter Lab. And if you look at the distribution of the NDWI values within your area of interest, and you have this histogram on the right, and you see that for most of the pixels, the values are below 0, even below minus 0.2. And there is just a few pixels here on the right below the arrow, which corresponds to the water pixels. So there is a nice and discrepancies between the water pixels and the non-water pixels, and from that we can determine a filter to create a mask of the water pixels of the water polygons. Of course, there are also some pixels which are considered as water, while it's not really water. So we calculated the surface of each of the polygons using the GeoPandas library. So then we have this output for each polygon. For each polygon, yes, we have the surface in a square meter or in hectares. If the surface of the water was below 4 hectares, then we consider that it was not a water reservoir. Of course, that can lead to some errors, because if you have an important reservoirs which is drying out, then you can be below this threshold. So it's important to be careful with this condition. And you can also export everything in a shapefile to use also, for example, in QGIS or in ArcGIS. Then once we have this method to calculate the surface of each polygon, we can consider the temporal evolution. Here we consider as a start only a 1-year period. And we use the cloud mask that we built it before to see if there was some intersection between the cloud mask and the water surface. Because of course, if you have a cloud like in the for half of the lake, then you will have a drop in the water content, but which is not actually the case. It's just because of the presence of the cloud. So we need to reject that from our time series. And then we can export everything in shapefile or in a CSV file. And here are first results for one of the water reservoir. You can see on the left the different colors are for the extent. And on the right, well, if there are below the red things, you have the the evolution of the water surface. So if you have a surface of 0, it's not because the lake is empty, but it's just because it's an image with too many clouds to be considered in the time series. So that should be removed from the time series. And so you can see a very good, you can clearly see the trends of the water content from this for this reservoir. Here is another example here, and shows you see the similar trend, even if the increase of the water content was a bit faster in this case. So yeah, this is a simple method because we wanted to have a simple method, and with already promising results using the Copernicus data space ecosystem. We see also that with the Sentinel-2 data, we have already a good temporal coverage to have a good monitoring. There is still the problem with this volume of the water content, which is not known with this method. So there are different ways to retrieve the volume, but the best way is actually to calculate the height being on site, which is not practically it's not very easy. So another option is to use topographic data, but that leads also to some uncertainties. And then the next step will be to operationalize that method and to automatize it, so over the whole watershed, and also to have a tool we can, at every new Sentinel-2 image, make an update of the water content evolution, and so that the users, potential users, can have good monitoring of the water content in each of the reservoirs. And thank you.